Alright, I have to start off by saying that this is a project that turned out to be much more challenging than I'd anticipated. I figured a robotic arm would be simple and straightforward, but I was very, very wrong about that. Over the course of my research, I determined that this would likely be a multi-part series due to all that is involved in a robotic arm. The human arm is a marvel of biology that is truly intricate and complex. What made my research into robotic arms so challenging was understanding just how difficult it is to mimic the anatomy and movement of the human arm. My goal with this video series is to break down the fundamental aspects of robotic arms and show how they pertain to the field of humanoid robotics. We'll start by going over the elements of a robotic arm: the base, the links, the joints, and the end effector. The base is the origin of the rest of the robot arm and is where the rest of the links of the robot emanate from. The links themselves are the solid members of the robot and are connected by joints that allow the arm to move. These links form an open kinematic chain, whereby the tip of the arm is free to move, unlike a closed kinematic chain. Lastly is the end effector, the portion of the robot that directly interacts with the environment. In industrial applications, it is often called the tooltip. In the world of robotics, you'll often hear the phrase degrees of freedom. So what does this mean exactly? Degrees of freedom refer to the dexterity of the robot, that is, how many different ways that it can move. How a robot moves is determined by its joints. Now, while there are a number of different types of joints that can be used in a robot's design, for our purposes, we'll be focused on robotic arms with revolute joints only. Revolute joints are the most common joints found in a robot and have a very simple purpose: hinge-like movement. In other words, revolute joints can only rotate. When a robotic arm is called a 6 degree of freedom robot, it means that it has 6 different hinge-like movements in its design, or more simply put, 6 motors. So far, I've been going over industrial robot arms, the kind you'd see in a factory. But we're interested in humanoid robots, not industrial robots. The reason I've been discussing industrial robotic arms is because they form the basis of how a humanoid robotic arm would work. Let's make the connections between the two, starting by understanding the human arm. The human arm has 3 joints: the shoulder, elbow, and wrist. It also has 7 degrees of freedom. That is, 7 different ways it can move. So where exactly do these degrees of freedom come from? The shoulder is a ball and socket joint that allows the shoulder to move in 3 ways: up and down movement, side to side movement, and rotational movement. The elbow is a hinge joint with 1 degree of freedom, which is only for bending the arm. The wrist is an ellipsoidal joint, which is very similar to a ball and socket joint, but it only allows for 2 degrees of freedom, which are up and down movement and side to side movement. We can also turn our palm up and down, and this is allowable because of the radial ulnar joint in our forearm, thus giving the arm its 7th degree of freedom. The human arm can be said to be a 3-link kinematic chain, the links being called the upper arm, which is the link between the shoulder and the elbow, the forearm, which is the link between the elbow and the wrist, and the hand, which is treated as the link between the wrist and the tip of the hand. Now, many robotic arms typically have 6 degrees of freedom instead of 7 like the human arm. The reduced degree of freedom is in the shoulder, where the robot will house 2 motors instead of 3. But why? Simply put, 2 degrees of freedom are easier to work with and often suffice for the movement needed for a fully functioning robotic arm. The elbow is the 3rd joint in the kinematic chain and allows hinge-like movements between the upper arm and the forearm. The wrist is often given the most dexterity in robotic arms due to the need for more dexterity in industrial applications, where it helps position the end effector for precise interaction with the environment. Now for the end effector. In most industrial applications, the end effector is typically a tool or gripper, depending on application. As it applies to humanoid robots, the end effector is going to be a robotic version of the human hand, which I discussed in my previous videos where I covered robotic hands in greater detail. In a sense, the arm's job is to position the hand such that it is able to interact with its environment in a highly dexterous way. And with that, we've covered the basic aspects of a standard robotic arm and how it can be likened to a human arm. Let's move on to how to make the robot actually move.
Now we move on to kinematics. Kinematics is best described as the motion of objects without worrying about external forces. In more technical terms, it is how we can mathematically describe how something is able to move. And when it comes to emulating a human arm, there is a vast amount of math involved. Think about it this way. When you want to position your arm in a certain way, say for example waving to someone, do you think about the angles that each of your joints needs to make to create that position? What if I go even more complex than that? If you want to pick up an object off of a table, do you calculate where it is in 3D space and then calculate what angles your joints need to have in order to reach that position? Those examples are the essence of kinematics as it applies to robotics. Kinematics is broken down into two categories: forward kinematics and inverse kinematics. Both tasks require a strong background in trigonometry and linear algebra. Understanding both is critical to making a robot arm move, regardless of whether it's an industrial robot or a humanoid robot. Kinematics serves as the connection between the two and will serve as the basis for making a humanoid arm. We can begin by taking a look at the topic of forward kinematics. This is a process that answers one simple question. If I know the angles of all the joints in my arm, where does the center of my hand end up? More specifically, where does the center of my hand end up relative to some origin point? Typically, that origin point is the base of the arm. Now when it comes to forward kinematics, it is much simpler mathematically compared to inverse kinematics. As long as we can decide what joint angles we want, there is only one correct answer to the question of where the hand will end up. There are several elements of math, including the Dennevit-Hartenberg parameters and the transformation matrix, both of which are used in combination with this formula. We'll go over this in more detail in another video, but this equation models the end position of the robot as long as we know the angles of the joints. Inverse kinematics is a much more challenging problem. As this topic applies to humanoid robots, defining the position of the hand in 3D space relative to the shoulder is what inverse kinematics are all about. Anytime the robot picks up an object, this is an exercise in inverse kinematics. Basically, if I want my hand to move to a specific location, inverse kinematics will calculate the angles all of the joints in my arm need to make in order to reach that position, given of course that the point in question is actually within my reach. Now here's an interesting thing to think about. The movement of the arm can be described by simple geometry. Picture for a moment that there is a point in the center of your shoulder, in the center of your elbow, and the center of your hand. You'll find that no matter how you move the arm, those 3 points create a triangle. Knowing where the starting point, center point, and end point are, along with the distances between, are all the information we need to calculate the joint angles of the arm at a specific endpoint position. This is the geometric approach and is the simplest method of calculation to understand, but also the simplest in execution. But it gets more complex than that. The problem is there is no one-size-fits-all equation for inverse kinematics. Multiple different approaches to inverse kinematics exist, which are geometric, analytical, and numerical, each progressively more complex. Within each of those computational methods, multiple solutions exist. In some cases, no solutions exist, or even solutions that would be impossible for the arm to put itself in. All of these considerations play a role in the topic of inverse kinematics and the development of any robotic arm. With a basic introduction, we can summarize the concepts of forward and inverse kinematics with these two simple statements. 1. Forward kinematics go from known joint angles to an unknown target position. 2. Inverse kinematics go from a known target position to unknown joint angles. These are the underlying concepts of an industrial robot arm, and they are the same ones that can be applied to a humanoid robot. It's simply a matter of applying them to such a robot.
When it comes to a robotic arm, there are many considerations that need to be addressed to get a complete picture of the wide range of use that an arm has, many of which are beyond the scope of this video, but I do plan to address in future videos. Additional topics that are critical to the development of robotic arms are the following: the velocity and acceleration of the joints and end effector. Velocity of the end effector is known as instantaneous forward kinematics and instantaneous inverse kinematics. Paying attention to the acceleration of the joints is also critical to smoother and less jerky motion. Improvement in both of these areas will also help with precision-based tasks. Singularities. A singularity is a position the arm is in that inhibits movement of the arm. A loss of a degree of freedom is critical to understanding how to make the robot arm move more efficiently and could potentially prevent the robot from damaging itself. Forces and torques. As the robot executes various movements and commands, it will generate forces and torques which can affect how it needs to interact with its environment. Without understanding the forces the robot is generating, it cannot effectively work with its environment and could potentially damage itself. Payload. The payload is how much weight the robot can lift. Technically, this is addressed by understanding the forces and torques, but I listed it as a separate task as it is of particular interest in terms of creating a robot arm with functional application. The workspace. Every robot arm has an imaginary sphere around it that represents the effective range of the robot. This means that the robot can touch any point within this 3D space. Knowing what this workspace is plays a critical role in safety and helps us understand how the robot interacts with its environment. Motion and trajectory planning. This is a more advanced form of movement where we consider the path we want to move the robot through, whether to avoid obstacles or to move through the shortest path in space.
The purpose of this video was to give an introduction into the complex topic that is robotic arms. Going into it, I knew the topic was going to be challenging, but the more I went through it, the more I realized just how complex this topic actually is. It took me a while just to understand the topic of inverse kinematics alone. With the amount of information there is to learn, I couldn't possibly cover this topic in one video without extensive months or even years of research. My goal for the next video is to build a robotic arm and to show applications of the concepts mentioned in this video. After doing so, I plan to apply those same concepts to a humanoid one. The goal in doing so is to show the connections between the two as I work toward my ultimate goal of creating a fully functioning humanoid robot. Join me next time on my journey as I delve deeper into the programming and kinematics of robotic arms.